Good morning. Myself Saanvi Rastogi, roll number 205004, and today I am going to explain the topic theory of equilibrium. Introduction. Equilibrium means a state of balance, especially between forces or influences that are working in opposite ways. A structure is in equilibrium when all the forces or moments acting upon it are balanced. This means that each and every force acting upon a body or a part of the body is resisted by either another and equal opposite force or set of forces whose net result is zero. Conditions of equilibrium. The sum or resultant of all the external forces acting on the body must be equal to 0. The sum or resultant of all the external torques from the external forces acting on the object must be 0. Now, types of equilibrium. First is stable equilibrium. A body is said to be in stable equilibrium if it comes back to its original position when it is slightly displaced. When a body which is in stable equilibrium is disturbed, its center of gravity is raised. For example, a marble kept in the bottom of a bowl. Unstable equilibrium. A body is said to be in unstable equilibrium if it does not come back to its original position when it is slightly displaced. When a body which is in unstable equilibrium is disturbed, its center of gravity is lowered. For example, when a marble is placed on a hill. Third is neutral equilibrium. The kind of equilibrium of a body so placed that when moved slightly is neither tends to return to its former position nor depart more widely from it. The center of gravity here is neither raised nor lowered. For example, a marble lying on a horizontal surface undisturbed. Now we come to application of theory of equilibrium. Equilibrium of strings. If the weight per unit length of the chain or string is constant, the catenary is called the uniform or common catenary. Equation of common catenary. From the figure we will get that let ACB be a uniform heavy flexible card attached to the 2 points, that is A and B, at the same level. C being the lowest of the chord, draw CO vertical, OX as horizontal, and take OX on x-axis and OC on y-axis. Let P be any point of the string so that the length of the arc CP is equal to S. Let W be the weight per unit length of the chain. Now consider the equilibrium CP of the chain. The force acting on it are tension T naught acting along the tangent C, which is therefore horizontal, tension T acting at P along the tangent at P, making an angle psi with OX. Its weight WS acting vertically downwards to the center of gravity of the arc CP. For equilibrium, these all forces must be concurrent. Hence, the line of action of the weight Ws must be passed through the point of intersection of T and T naught, resolving the horizontal and vertical. We have T cos psi is equals to T naught, T sin psi is equals to Ws, then tan psi is equal to sin psi upon cos psi, then Ws upon T naught. We shall write T naught is equals to W equal to C, where C is the constant. Therefore, tan psi is equals to S upon C, then S equals to C tan psi, which is called the intrinsic equation of the catenary. We know that the relation dy upon ds equals to sin psi and dy upon dx equals to tan psi. Now dy upon d psi is equals to dy upon ds multiplied by ds upon d psi. Here we have multiplied and divided by ds, which is equal to sin psi c sec square psi, which is equal to c sec psi tan psi. Now integrating we get y is equals to integral sec psi c tan psi d psi, which is equals to c sec psi plus a is the constant. If y is equals to c, when psi is equals to 0, then c is equals to c sec 0 plus a. Therefore, a will be 0. Y is equals to c sec psi. On multiplying both the side, on squaring both the side, we get y square is equals to c square sec square psi equals to c square whole bracket 1 plus tan square psi, which is equal to c square plus s square. S square is written as y square minus c square. We know that dy upon dx is equals to tan psi, which is equal to s upon c, then under root y square minus c square upon c. Dy upon under root y square minus c square is equal to dx upon c. On integrating both the side, we will get cos hyperbolic inverse y upon c is equal to x upon c plus b, which implies y is equals to cos hyperbolic x upon c. This is the Cartesian equation of common catenary. Now we come to system of forces and its types. A force system is a collection of forces acting at specified locations. Thus, a set of forces shown on any free body diagram make up a force system. Force system is simply a term used to describe a group of forces. Type of force system: coplanar force system and non-coplanar force system. The force system in which all the forces acting in the same plane is known as coplanar force system, whereas system in which the forces acting in different planes is called non-coplanar force system. Concurrent and non-concurrent force system. The forces which are passing through a common point are called concurrent force system, whereas the force which are not passing through a common point are called as non-concurrent force system. Now we comes on Poisson central forces. A line through a rigid body which is parallel to the vector sum f of the force system of forces acting on the body, and which is located so that the system of forces is equivalent to the force f applied anywhere along the line, plus a couple whose torque is equal to the component of the total torque T exerted by the system in the direction of force F. Central force: if a system of forces reduced to a single force and a single couple in such a way that axis of couple coincides with the line of action of the force, then the line is called the central axis. Wrench and pitch: if a system of forces is reduced to a single force R and couple having moment K whose axis coincides with the direction of the forces, then R, K is called the wrench of the system, and the ratio K upon R is called the pitch of the system. Screw: a straight line along with the acting force which considered together with the pitch is known as a screw. Now we comes to application of theory of equilibrium on system of forces and points and central axis. Condition of equilibrium of a rigid body: if the force F1, F2 till Fn are acting at A1, A2 till An respectively on a body, so we can reduce the system into a single force R acting at an arbitrary point O and a couple having moment G whose axis pass through the point O. Then we have R equals to summation I equals to 1 Fi, comma G is equals to summation I equals to 1 AI into Fi, which will be equation 1, where AI is the position vector of AI. For equilibrium of a body, we have R equals to 0 and G is equals to 0. If I has component Xi, Yi and Zi, then Fi is equals to I cap Xi plus J cap Yi plus K cap Zi, which will be equation 2. Now let AI equals to A cap Xi plus J cap Yi plus K cap Zi, then we have summation I equals to 1 Fi equals to 0 implies summation I equals to 1 bracket I cap Xi plus J cap Yi plus K cap Zi equals to 0, which implies I cap summation I equals to 1 Xi plus J cap summation I equals to 1 Yi plus K cap summation I equals to 1 Zi equals to 0, which will be considered as the equation 3, which implies x equals to 0, y equals to 0 and z equals to 0, where x equals to summation I equals to 1 is xi and y equals to summation I equals to 1 I cap and z is equals to summation I equals to 1 zi. The determinant of xi into fi is given here as I cap bracket yi zi minus zi yi plus j cap zi xi minus xi zi plus k cap xi yi minus yi xi. From here we get summation I equals to 1 ai into fi equals to 0, which implies xi summation I equals to 1 I cap yi zi minus zi yi plus j cap zi xi minus xizi plus k cap xiyi minus yixi equals to 0. Let summation I equals to 0, I cap yi zi minus zi yi equals to L, and m be equal to summation I equals to 1 j cap yi zi minus zi yi, and n as summation I equals to 0 k cap xi yi minus yi xi. Then we have I cap L plus m j cap m plus k cap n equals to 0. From here we get L equals to 0, m equals to 0, and n equals to 0. From the equation 3 and 4 we get x equals to 0, y equals to 0, z equals to 0, and similarly L and m and n equals to 0. These are the conditions for the equilibrium. Now we come to virtual work and application of theory of equilibrium on virtual work. Virtual work, which is written as delta W, is the imaginary work done when a particle subjected to a number of forces is moved a small imaginary distance, that is del U. The necessary and sufficient condition that a particle acted upon a number of coplanar forces be in equilibrium is that the sum of the virtual works done by the force in a small displacement consistent with the geometrical conditions of the system is 0. Virtual work done by the system of forces F1, F2 till Fn are alpha x1 plus beta y1, comma alpha x2 plus beta y2, comma alpha x3 plus beta y3 till alpha xn plus beta yn. Therefore, alpha x1 plus beta y1 plus alpha x2 plus beta y2 plus till alpha xn plus beta yn equals to 0. Then alpha x summation x plus beta summation y equals to 0, which will be equation 1. From the theory of forces, sigma x plus is equals to sigma y will be equal to 0. Let the new position of 0 dash is alpha dash comma beta, which implies alpha dash summation x plus beta summation y equals to 0. Here comes the second equation. From subtracting equation 2 from equation 1, we get alpha minus alpha dash summation x equals to 0, but alpha minus alpha dash not equal to 0. Then we get summation x equals to 0. Similarly, we can prove for summation y equals to 0. Thank you.